In July 2022, the James Webb Space Telescope sent back its first images of the deep universe. Physicists expected to see what 50 years of cosmology predicted: small, primitive galaxies still in the process of forming. The universe was only a few 100 million years old. The model said large structures take time to assemble, that massive galaxies are the product of billions of years of mergers and matter accumulation. What they found was the opposite: fully formed massive galaxies, with stellar masses comparable to the Milky Way, in a universe that was still an infant. The reaction from astrophysicists wasn't celebration, it was confusion. And a researcher at the University of Kansas, Allison Kirkpatrick, said something you almost never hear in science. I went home and thought, I might have gotten everything wrong. And there's one specific galaxy the physics community has been quietly avoiding in official press releases, because if its data holds up, the problem isn't just that the model is off. It's that the universe operates in a way no current model can explain. Here's what we're going to work through. What Webb found that breaks the standard model of galaxy formation, the 4 hypotheses physicists are using to try to explain it, and which one is the most unsettling, and the question that connects everything: if the standard model is wrong, what else we think we know could be wrong too? Stick with me. The most disturbing data point isn't the impossible galaxies. It's what the math says about the matter that would have had to exist to build them. To understand why the Webb findings are so disorienting, you need to understand what physicists expected to find. The Lambda CDM model, standard cosmology, the framework that describes the universe from the Big Bang to today, makes very specific predictions about how galaxies form. The process is hierarchical and slow. Dark matter halos form first. Normal gas falls into those halos, cools, and starts forming stars. Small galaxies merge into larger ones. The whole thing takes billions of years. Under that model, in the first 700 million years of the universe, the period Webb can actually observe directly, galaxies should be small, irregular, sparse, and actively assembling. That's what every previous telescope had confirmed, within the limits of its resolution. Webb has infrared sensitivity and resolution that nothing before it has matched. It can see farther and in more detail than anything we've ever built. And when it pointed at the early universe, it saw something the models said couldn't be there. A paper by Ivo Labe and his team, published in Nature in February 2023, identified 6 galaxy candidates at redshifts above 7.4, meaning we're seeing them as they were when the universe was under 700 million years old. Their estimated stellar masses, between 1010 and 1011 solar masses, 10 billion to 100 billion times the mass of our Sun. The Milky Way has roughly 5x 1011 solar masses in stars. Some of these galaxies are comparable, in a 700 million year old universe. The problem isn't just that they're large, it's that the dark matter halos that could have hosted them at that point in cosmic history weren't massive enough to contain that much stellar matter. The galaxies are bigger than the containers that were supposed to have built them. Mike Boylan-Colchin at the University of Texas at Austin calculated the direct implication in a 2023 Nature Astronomy paper. For those galaxies to exist as Webb observes them, the star formation efficiency in the early universe would have had to be 100% or higher. Every single bit of available gas in those halos converting into stars. No waste, no dispersal, nothing escaping. In modern cosmology, typical star formation efficiency runs between 5 and 20%. He called them universe breakers. But that's not even the wild part. The problem wasn't just that the galaxies were too large, it's that they were too quiet. In 2023, Catherine Glazebrook's team used Webb spectroscopy to confirm a galaxy called GS 9209 at a redshift of 4.66, placing it when the universe was only 1.8 billion years old. GS 9209 had a stellar mass of 4x 1010 solar masses, and it had stopped forming stars, a dead galaxy, in a 1.8 billion year old universe. Under the standard model, a galaxy that size shouldn't have finished forming by that age, let alone burned through its gas supply and shut down star formation entirely. A dead galaxy in the early universe is like finding a 90-year-old who was born 15 years ago. The numbers don't work. Physicists have 4 hypotheses. None of them fully resolves the contradiction. 1. Dark matter behaves differently than the model assumes. If dark matter can interact with itself, called self-interacting dark matter, halos could concentrate faster and more efficiently, allowing more massive structures to form earlier. No particle physics experiment has confirmed this behavior. 2. Star formation efficiency was simply higher in the early universe. If the first stars, population 3 stars, were far more massive and luminous than today's, and if primordial gas converted to stars far more efficiently, the observed masses become reachable. But this requires a primordial stellar physics without precedent that nucleosynthesis models don't easily predict. 3. Dark energy isn't constant. If the expansion of the universe varied in its early stages differently than lambda CDM assumes, the timeline for structure formation shifts. This connects directly to the 4th hypothesis, and the one physicists are being most careful about. The Hubble tension. The Hubble constant is the rate at which the universe is expanding. Measured from the cosmic microwave background, the oldest light we can observe, it gives 67.4 kilometers per second per megaparsec. Measured from nearby distances using Cepheid stars and type Ia supernovae, it gives 73, a 9% discrepancy. Webb was partly designed to resolve that gap. Its Cepheid measurements published in 2023 confirmed the value of 73. It didn't close the tension. It pushed it to 5 sigma statistical significance. In physics, that's the threshold for declaring a discovery. And here's what nobody is saying loudly in official communications. If the universe is expanding faster than the CMB-based model predicts, the universe could be younger than we calculated. If it's younger, the impossible galaxies Webb found become even more impossible. Because there'd be even less time than we already know isn't enough. The galaxy nobody is mentioning much in official press releases is a candidate at redshift above 16 detected in the JD's deep field, which, if spectrally confirmed, would place a massive galaxy when the universe was under 200 million years old. The team is being extremely cautious before publishing spectroscopic confirmation. Because if it's real, it's not an anomaly in the model. It's the collapse of the model. No joke, the lambda CDM framework is the most successful model science has ever produced for describing the structure and evolution of the universe. It predicts the galaxy distribution, the temperature of the cosmic microwave background, the abundance of light elements. It has passed decades of tests with extraordinary precision. And the telescope built to confirm its most precise predictions in the early universe is finding instead that something doesn't fit. Not in one data point, in several independent signals, all pointing the same direction. The early universe was more structured, more massive, and more active than any current version of the model predicts. That doesn't mean all of physics is wrong. It means something in the model, dark matter, dark energy, the Hubble constant, stellar efficiency, or some combination, needs revision in a way we don't yet know how to make. The last time physics had to fundamentally revise its model of the universe was 1998, when accelerating expansion was discovered and dark energy was introduced. That won the Nobel in 2011 and reshaped cosmology entirely. Webb may be pointing to the next revision. Do you think we're at the beginning of a physics revolution? Or will the standard model survive with adjustments? Drop it in the comments. And if this video changed how you see the universe, subscribe. Next week, the Hubble tension in detail. Why 2 measurements of the same universe give incompatible results and what that might mean.